What we're going to be going over here is a linear regression line, and we're going to be using least squares method here for fitting a linear regression line. And what we're going to be doing here is we're going to be calculating the formula or the equation that represents a linear regression line here. Okay, so this is what we're dealing with when we're talking about regression lines, in particular linear regression lines, because a linear would be a straight line here. What you're going to have here, and we'll start out with our graph here. Along our x-axis on our graph, you're going to have some independent variable here. And then along our y-axis on the graph, you're going to have some dependent variable. So your y value here depends on whatever your x value would be here. So you want to represent those y and x values by some what they call here a regression line here. So for our case here, let's just say you're going to have some actual results for your x and y values, and you'd have any number of those x and y pairs here or actual results here. So what you want to do here is you want to estimate a line, or you want to determine a line that represents those data here. And this is about how we go about doing it here. So let's just start out, and we'll look at, we'll go through just 3 points here, 1, 2, and up to n points here. But you'd have any number of points here that you'd be dealing with. But this is the general technique that you'd be using here. So let's just look at our first point. Our actual first point here, it would be an x1, y1 value here. So it can have some x value here. And for the x value, you're going to have an associated y value over here. So that would be your first point here, x1 represented by x1, y1. And then you're going to have a second point here, x2, y2, sitting up here, some y value here, some x value here. And then you just move on and up through any number of these different points here. So we'll get to we'll look at it in terms of our last point here, it'd be xn, yn, however number of points you're going to have here. And again, you're going to have some value for that here, represented by your x value and your y value here. Okay, so now we can go, and what we have to do here, if we can calculate a line here that represents this data here, and it's going to be, again, what they call a regression line here, and in particular a linear regression line here, because it's straight. We assume that we can represent this data here by a straight line here. So really what this line is here, let's understand that here. Y, this is just the general formula for a line. Y equals mx plus b. Well, what is m here? M is the slope of the line here. This is because of general algebra equation here for a line. M is the slope. So really what the slope is a change of y over the change of x. That is, whatever change you have in y here, you'd have a representative change in x here. So that's your slope here. In terms of x here, you go over so many units of x, and then you'd go up so many units of y here to represent your slope. And then the other item here on a line is the b value here, and really that's what they call the y-intercept here. This is where your x value is set at 0 here. You're going to have some b value here that represents your y amount here. So it's going to cross the y-axis here at the x-axis equal to 0. So the key is here to represent this line. If we can represent, determine our y-intercept, or where it crosses the y-axis when x is equal to 0, and the slope of our line here, then we can determine the line, and we can predict our different values here. Predict the value here, y equals to m. Whenever we know x here, we just take y equals the slope of our line here times our x value plus whatever our y-intercept would be. So that would be our predicted y here. That's what we're looking at. So when we're working with linear regression here, we're dealing with errors here. So for our first, and look at it in these terms here, our error 1 here. So we have an actual amount for our x and y values here, x1, y1. And then we move directly vertically up here, and we're going to, on our line here, we're going to have a point that we're going to be looking at here. And that's going to be our y value here. This is going to be our regression value here, our predicted y value here. So our error here, looking at error 1, our actual amount here is y1, whatever we're looking for, that y error here. y1, that's the actual y that we have, less that error. The difference is, our predicted y here is mx1 plus b. So what we're going to do here is just subtracting y1 minus our predicted y here, mx1, because y is predicted by based on whatever the x value is here, plus b, the y-intercept. So what you're going to do here is just take the difference between those two. The actual y here, y1, minus the predicted y here, mx1 plus b. And then you want to take that difference here, that quantity that you have, or that difference here, and you want to square it. They square it to get rid of any negative values here. So that's what we're defining our errors here. So we defined our errors by knowing our actual point versus our predicted point, and that difference determines our error. So we're going to have an error 1 here for x1, y1. We're going to have an error 2 here for x2, y2, and then on up the line here. So when we get to xn, yn, we're going to have an error error n here for xn, yn points. So the deal is here with regression here, if we can minimize this error here, that fits our regression line here. So whatever total error we have here, error 1, error 2, error 3, 4, 5, up through error n here, we total those errors up here, and we can minimize those errors. And you would do this really with a computer, but we're just looking at the algorithm here for developing this line here. So you would do that here through usually some software program or something of that sort. But nonetheless, we're looking at how we calculate the slope and the y-intercept of this line. So what you want to do is you want to minimize that your error here. Those total error, you want to minimize it. So let's go and let's look at how we do that here. Okay, so this is what you're going to look at. The total squared error here, I represented by SC. That would be the total squared error here for the line here. That is the line that we're looking at here. So what we want to do, we want to look at that error here. Error 1, remember we talked about that. That was your y1, your actual value, less your predicted value here, m, slope of the line, times whatever your x value is, plus b here. And then you would take that difference here, the difference between those, the actual y and the predicted y, you would multiply or raise it to the power of 2 here to get rid of any negatives here. And you would move on down the line here. You do the same here for your error 2 here, y2 minus mx, mx2 plus b here, that value squared, and on so here. You get down to yn plus slope here, xn plus b here. And that value squared. So you're dealing with your actual y here that you have versus what you're predicting here through your line equation here. So what you want to do is you want to total, you would be totaling all those errors up here, and this is going to give you the total squared error of the line here. So what you're going to do here, and we're not going to do it, but just to explain what's going on in this equation here, you would take, and taking all those, your values here, you would total them up, and you're going to do an algebraic manipulation. Really, you're going to expand that equation here that's represented by that, and it takes a lot of hand work to do that here. And then again, make a point here, those x and y values that we're looking at, when we're going to, they're really mean values after we expand this equation here. And we'll get into that here when we look at the formula. So this total squared error here of our line, after we would expand or do our algebraic manipulation and expand this our equation up here, or our representing our errors up here, you're going to come up with a value that's going to be like my squared here minus 2mn times the quantity xy here. And I'm going through this here just to, if you're interested in doing it, you'd come up with this value here. And then minus 2b here, y, plus m squared n to the x squared here, plus 2mm bn x plus nb here. So expanding this, our total squared error equation up here, or those values here, we're going to come up with some equation here. And just remember, there's x and y here are mean values here. Okay, so what do we do with this here? So this is an important key here. So to determine, what we want to do is we want to solve for m and b here at their minimum amount here. So that's is where we fit that line here, those line points, to this equation here. So we want to solve for the minimum total squared error here for the line here. So really, what we can look at for our m and b values here, it's really represented. We're going to look, and this we'd be doing through algebra up here. All this manipulation is done through algebra. But now we get down to coming up with the minimum values here for m and b here. This is where it's going to involve some calculus here. So what you're really looking at here, you're going to have like a 3D parabola here, or a 3D axis here, where you're going to have, if this is the calculus that's involved here, you're going to have an m axis, the slope axis shown here, and then you're going to have your b axis here, the y-intercept coming in here, and then we're going to have that third dimension here. That would be the total squared area of the line here coming up here. So really what you come up with it, if you look at that squared area of the line through your algebraic equation here, you're going to have some parabola here, and it's really rotates around this squared area here of the line. And what you're going to do here, using our calculus, if we take the partial derivative here of our squared area of our line, this algebraic equation here, we can come up with the minimum point here that's going to represent our m and b values here. So we're dealing with this 3D parabola, and we want to minimize both our m and our b values here. And we do it through partial derivatives here of the total squared area of the line here. So we're going to take a partial derivative of our squared area of the line here with respect to m here, the slope of the line, and we set that equal to 0. That's going to represent our minimum point. And then if we take the total, or the partial derivative of the line here, SE, with respect to b here, or the y-intercept, set that equal to 0. So that's going to give us our minimum points here for m and b here. Okay, that's the general procedure that we do it, and it's interesting just to know how they came up with the formula here. We're only looking at this in terms of how they developed the formula here to represent that linear regression line here. Okay, so let's go up and let's look at the results that we would get. Okay, up here, so if we did a partial derivative of m here, our slope set equal to 0, and we're looking at it just in terms of these x and y values. There are mean values here, and we'll look at them in terms of our equation here. But okay, for m here, we'd come up with this equation, minus xy plus mx squared here plus b times x equals 0 here. So we can just rearrange that equation to look like this here. And then for our partial derivative here for our b here, or that would be our y-intercept here, you're going to get a minus y plus mx x plus b equals 0. Just rearrange the equation here. So you get these two equations here for our partial derivative for our slope here, mx squared plus bx equals xy here, and then for our y-intercept, mx plus b equals y here. So we've got two equations here and two unknowns. So really, when you solve it, you're going to come up with something that looks like that. And that's going to be for our m slope here. And we'll detail that now. Okay, so that is our partial derivatives here and how we came up with our general equation here. Okay, so now this is the regression line, the fitted here. And this is really what you would be looking at here. And this is the key to the whole thing here. You'd go through that algebra manipulation. You don't have to. I'm just showing how these formulas came into play here and how we developed our different formulas here to determine both the slope of the line here and your b-intercept here. So what you would be doing here when you actually do your calculations, let's look at it. We got m, our line slope here, showing it. We're going to have a quantity up on top here, and then it's going to be divided by a quantity up on the bottom here. So let's understand what we're talking about here. And this squiggly thing here, that's really a summation sign, or that we'd be summing some values for. So what you would do here, those equations that we came up with here, we take the mean of the x's here, and what we talk about the mean of the x's here, 1, 2, that we'd sum up your x values, x1, 2, 3, 4, 5, and 6, up to whatever, up to n number that we're dealing with here. See, that with the mean of the x's is whatever you sum all your x values and you divide it by n. N is the number of observations that we're looking at here for those x and y observations here. And then you take your mean of the x's, you take that, whatever that value is, you take it times the mean of the y's here. And what we mean by the mean of the y's is, again, you sum up your y values, y1, 2, 3, 4, 5, and 6, up to yn values here. And you divide those by the number of observations. So that gives you your mean of the y's here. So you take your mean of the x's here, whatever that mean is here, times your mean of the y's here. And that's what that little equation that we have here. You multiply those together here. And then you would take whatever you multiplied together here, you'd subtract the mean of the xy's here. And what we mean by the mean of the xy's here, again, you take x times y, x1 times y1, and then you sum it. You take x2 times y2, whatever value you get there, add it to the x1, y1, and then you take the next value, x3, y3, and then you'd add those, you'd sum those, whatever your x times y, whatever value you get for that quantity, you keep on summing it for 1 through whatever n value is looking for. And then you divide those by the number of observations. So that gives you, understand it. So you get the mean of the y's here, and you would subtract the mean of the y's here, that whatever value you get here, from your total value here. The mean of the x's times the mean of the y's here. Subtract that, and that gives you your numerator value here. And then in your denominator, what you'd have here again, you take the mean of the x's squared. And what we mean by that is, remember, we sum our x's here, x1, x2, x3, keep adding those up here until you get the xn. And that total value, whatever total value you have, you would square that value. Again, but it has to be divided here by the n here. You would have to divide it by n here before you do your squaring. Just remember that. And then that's your mean of the x's squared here. And then you would subtract from it the mean of the squared x's here. Okay, so what we mean by the squared x's here is that you would have, again, you would x1, you would square that. Then you would add to it you get your x2 here, you would square that and add that to your square of the x1. x3, you would square whatever value you have for x3, and then you would add it to the squared value that you had for x1, x2, and you do that on up to n here. And just divide that by n, the number of observations. So this is your mean of the squared x's here. That's your mean of the squared x's. You subtract that here from the mean of your x's squared here. And then whatever your quantity have here, you divide that amount. The difference here goes into your whatever you calculated in your numerator up above here. Okay, so understand it. So just understand the relationship is, because you're going to have to deal with this if you have to understand or your calculations that you make down the road. You take your mean of the x's times your mean of the y's here. That quantity you would subtract here from the mean of the xy's here. And then what we mean by is n, whatever n observations you have here. And then that quantity here divided by the mean of the x squareds minus the mean of the squared x's here. So the big thing here is trying to understand your formula when you're talking about those different means here. And if you look at it in terms of the summation sign here, and you can understand what's going on here, how I have it laid out. Okay, so that's our m, our slope of the line here. Now, you would go through the same arithmetic here in algebra and so forth to determine your by or your let's look at it, the by-axis intercept. But rather than doing that, I'm just going to do a substitution here, because you'd come up with this summations and these algebras and everything here for your b-axis intercept. It would be something similar to that here. But through a substitution here, let's just look at, we know that b, or our y-intercept here, is going to equal, based on that equation, our equation here, it's y, after we solve for our equation here, y minus the slope of the line here times x values here. And these y and x's, let's look at those here. So our mean of the, what we do here for this equation, we have the mean of the y's, that's y1 through yn, or y1 plus y2 plus y3 and so forth up through yn. Again, divided by the number of observations, because that gives you your mean of the y's. And then you would subtract from that your m, your slope value. We calculated that up here. Okay, m, your slope value, times the mean of the x's here. So you're taking your slope that you calculated above here times the mean of the x's. And where's the mean of the x's? x1 plus x2 plus x3 up through xn here. again divided by your number of observations. Okay, so that's for your b or your y-axis intercept here. And I did it just through a substitution, but if you'd gone through all the algebra, you'd have to come up with some complicated equation like we had for the slope of the line here. Okay, all right, so the equations we went through here, we developed them, but to make a point of something here. Now, if you'd compare what I've done here with what you might have in your textbooks, so just to make a note, the textbooks may have these equations reversed. That is, whatever you had here on your right side would be sitting on your left side, and the left side would be sitting on your right side. Because these equations here are based on the actual algebra and the actual calculus that's done here. But they switch them around here, and numbers come out the same for your slopes and your y-intercepts. They switch them out looking at it in terms of a positive y, or positive sloping upward. So when you actually solve all these, your line and the slope, you're going to come up with negative value on your, let's just go look at it here. You're going to come up with some on your slope here. When you solve it using the equation I have set up here, you're going to come up with some, for a positive slope, let's say for a upward sloping, you're going to have some negative value up here, and you're going to have a negative value in your numerator here, and you're also going to have a negative value you're going to get in your denominator down here. But when you divide those out, the negatives into a negative, you're going to get a positive slope here, in the case here of a positive line. So that's all I'm trying to say here. If you're trying to compare it to a textbook example, these equations here may just be reversed here, but this is really, they're going to come up with the same results here. Okay, so we went through our solution here, and all we wanted to develop is based on that regression line. We wanted to establish that regression line, and now we have that regression line. We have our actual points here, and then our predicted values here. We can predict that, our model prediction here. We developed our slope. We determined what our slope of the line was here based on our predicted and actual amounts here, and how we got to these things here. Remember, we went through that partial derivative here for the the total squared errors of the line here. But this is the general formula that we're looking at here, both for our slope here and for our b or our y-intercept. I just use the substituting, whatever slope we calculate, we just substitute it in here. Okay, so that's our summary here on our linear regression line, calculating our formulas here. So if you just work off what I've shown here, and we can go through an example on another video here, but if you just get down to the end here and understand what I've looked at, mean of the x's, mean of the y's, mean of the y's here, what you're going to do is you first want to calculate all your different means of the x's, means of the y's, mean of the x, y's, and so forth. You want to come up with a list, and then you just plug them into your equations here. Okay, so that'll summarize our discussion here on linear regression line fitting using the least squares method here, and we calculated our formula here for doing that.